All right. So let's get started with project phase one presentation. So the aim of this phase was that to get the multi-thread processor up and running, integrated with the FIFO block to receive the packets, process them, and to run four different network processing programs on four different threads. Right. So we completed all those objectives, and here's the I'll just first run you through the overview of our system. So it's a simple system. We carried forward the previous system design itself and then built and made some modifications to that. So you receive packets from the previous block. Those packets are stored in the FSM, the FIFO block. So what happens is here, one thing to note is one individual packet is received first, and then it is processed, sent to the next block, and then the next packet is received, and then it's processed by the processor and then sent to the next block. So that's how it happens, right? So basically we built a finite state machine around a data memory element, right, to in order to implement this, right? So this is the overview of the system. So you can see this is the FIFO block, the FSM that's built around that. So that has the data memory element, right, a dual ported memory. So the port B is used for debugging during runtime, and the next block, the next port is usually used for other interfaces that are required, right? So what we see here is that this FSM is designed in such a way that it receives for one single packet from the previous block, and then it sets in underscore ready to 0 at the end of the packet so that it doesn't receive any further packets. Then after that it sends a signal to the processor saying that you can go ahead with processing the data, right? All of those the words of that one particular packet are stored in the this FIFO memory element, right? So that becomes the data cache for our processor. So our processor is a four threaded processor, right? It has individual PCs corresponding to the four threads and the corresponding register files, right? So after it receives the packet, after the FIFO block receives the packet and it sends the signal to the processor, it enables, right? The execution starts. Now in order for us to do some processing, we need certain information. So those information are stored in these particular registers that you see here: read pointer, write pointer, and depth. So the read pointer always points to the starting of the packet, that is the first word of the packet, right? And the write pointer always points to the empty bit, right? The end, right? The end of the packet and the next empty location of that. And the depth indicates how many words are there in that packet. So all these information are given to the processor. How it is done is read pointer is stored in register 29. The depth information is stored in register 28 of all the threads. Write pointer is usually not required. Write pointer is used for sending the data. For receiving the next particular data. So write pointer is information is not required for processor, right? So let's look at the finite state. Let's look at the Verilog implementation of this, right? So we built on the same simple pipeline to increase to quad thread, right? So we have individual PCs, PC0, PC1, PC2, PC3. We have a thread selector counter, right? So that keeps incrementing and saturates at 4. So corresponding to that, we are enabling each PC, and that is how we are accomplishing the fine grained multi-threading, the simultaneous multi-threading, right? So first you get PC0, then you get PC thread 1's PC, then you get thread 2's PC, and then the thread 3's. So the instruction cache is the same, right? So you can see that what we accomplished is we actually segregated the instruction cache into four different spaces in order to make sure that all of them are apart, right? All of the programs are apart. So it's basically segregating instruction cache into four different spaces, right? And then we have four different register files, and then apart from that, all of the other blocks are same: the execution stage, the memory stage. And here I have you can see that there is no data cache. So since I'm giving it to the FSM itself, right? So we are using the memory block of the FSM itself, we don't require that, right? So that has been done. And when it comes to finite state machine, I had explained in the previous lab how our FSM works. It works perfectly even on NetFPGA, so we carried forward with that. And also you can see here I've written code such that we can get the read pointer in store the read pointer in register 29, right? And same thing with here, we are storing the depth in register 28. So that's why we can run any sort of code with this information and do any processing using the these information on the network packets, right? So that is one such thing. And another modification we did was for register files, right? So we used block rams to generate the register files, thereby reducing the space. And you could see that the our utilization is just 9%, which is considerably low. Previous In the previous lab, our utilization was close to around 68% or 67%. Now it's 9%. That's a drastic reduction, right? So that is one improvement we did. And another improvement we did was regarding the branch. So during branch time, what we had was we had a one branch delay slot. That is, the instruction after branch also would get executed. That is why we had to put no up. Now that bug has been fixed, and that doesn't happen anymore. Yeah. So what happens is, after one particular packet is after the processor is done with all its processing, it will send a signal back to the FIFO block saying that I'm done processing. That is done through pi_di. So now the processor, what it does is, it kind of the processor kind of goes into a reset state, right? So we are flushing all the instructions that are there in all the stages, and we are setting everything back to their reset values. And also the data cache then goes to transmission state. So in the transmission state, we just use the read pointer to read out all the data to the next block, right? You can see that we have used mux for example. So for port A, in the idle stage and the reception stage, what we are doing is, that is being used by the netfpga controls, right? That is used to store all the words from the netfpga. That's why in_data and in_control are given. But during the execution stage, that is accessed by the processor, right? So that is why processor memory accesses should be given. That is mem address, mem write whatever the data in the mem write enable and stuff. Same thing with the d out. So in idle and reception stage, out data, out control are taking hold of the d out, so the output of the memory block basically. But in execution stage, that is taken care, that is got the processor basically gets the hold of it. And back in transmission stage, again, that is, the control is given back to out data and out control, right? So this is how we have implemented it. Now we are running 4 different threads, 4 different network processing algorithms. So one is about modifying the port of a port in case of a UDP connection. 2 are about modifying the actual payload itself, and another one is about modifying the IP address. So my teammate is going to explain further on these things. He's going to explain about the code, and he's going to explain and he's going to walk you through the simulation. And my another teammate is going to walk you through the netfpg implementation of that.
Hello everyone, this part is the packet analyzer. In this part, we use the previous FIFO lab to record a packet, a network packet. So assume this is the FIFO in the netFPGA. We will first record the pointer before sending a network packet, and after sending a network packet, we will record another pointer. So the differences of the pointer will be the space we save the network packet. And in our case, we have saved 3 kinds of network packet: TCP, UDP, and ICMP packet. And one point note to mention is that we need to do the recording 2 kinds of pointer and read all the memory location in one script. We cannot do it manually, because that after sending a network packet, there will be other packets sending inside the FIFO, and it may overwrite the original network packet. And this is the script we use to dump out the network packet. So in here, we will first read the pointer and record it as a start num. And after doing either pin or one UDP packet or one TCP packet, we will record the n number that the pointer of inside the n number. So between these two numbers, we can dump out all the memory, the network packet. So in here, this is the TCP dump we have. So it starts from 56 and it ends to 193. So in here, that this FF is the network packet, network control packet, and this is the payload, the data, and this is the control signal, and this is the data. So I think that there's a lot of FF here, yeah. And this is the UDP dump. Is similar, and this is the ICMP dump. Also, this is all the same. This is the data, and this is the control packet. Hello everyone. Since we have dumped out all the TCP, UDP, and ICMP packet, we can further analyze it. And now I'm going to analyze the UDP packet. This line and this line and this line till here is the NetFPGA header, so we don't care about that. We're starting from here. It shows the IPv version 4, and the 5 is the header length, so it means that it's 20 byte. And for the green one, it is 11. It shows that it is a UDP packet. And for here, this is the source IP address. It means that it is 10.1.0.2, and the blue one is the destination IP address, so it is 10.1.0.3. And here the blue line is the UDP header, and the red line is the payload. So for the UDP header, this is the source port, and this is the destination port. So the destination port is 8089, right? It's 8089. So in hexadecimal, it will becomes 1F99. Yes, and after this, all these 7s are the payload. So because that the ASCII code of W is 77 in hex, so there is like 10 W. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There will be tens of 77 here, and the 0A is the new line character. And let's analyze the TCP packet. I think it's very similar. The only difference is that the green one is it shows is a TCP protocol, and this is the source IP address, and this is the destination IP address. And I think the payload is the same. Hello everyone. Since we know the format of the TCP and UDP packet, we can now write assembly code for our 4-threaded pipeline. And for thread 0, we will write an assembly code to check if the source IP address is 10.1.0.3. If it is, it will be changed to 10.1.4.3. And for thread 1, if it is, it will check if it is a UDP packet. If it is the UDP packet, it will add 4096 to the destination port. So for example, if the destination port is 1F99 in this UDP packet, it will be added 1000, it will become 2F99. And for thread 2, it will change the first word of the payload from WW to FF. And for thread 3, it will change the second word of the payload from F to do the same thing. And this is the assembly code for changing the IP address. So basically, it's just do the bit max for getting the source IP address, and it will do the XOR to check if the bit max value is the same as 10.1.0.3. If it is equals to 10.1.0.3, it will change the memory, the data from 10.1.0, the source IP address from 10.1.0.3 to 10.1.4.3, and it will store it back to the memory location. And the source port, the assembly for changing the destination port and changing the payload is very similar. So for the simulation, we have read a test bench for simulating the four-threaded pipeline. This is the TCP packet, and this is the UDP packet. For TCP packet, because that it is not, the IP address is not 10.1.0.3, and also it is not a UDP packet, right? So all these four threads will do nothing. So the payload will not be changed. And for the UDP packet, because the IP address is 10.1.0.3, it is shown here 10.1.0.3, it will be changed to 10.1.4.3 after the simulation. And for the source port destination port number, it will be added from 1F99 to 2F99. And for the payload, the 7 here will be changed as 6 like this, and the 7 here will be changed it will be changed as 6 like this. And now this is the simulation. So for the simulation part, this is the UD input of the TCP packet, and this is the output of the TCP packet, and they are the same. And this is the input of the UDP packet, and this is the output of the UDP packet. So let's check the UDP packet. Yeah, it's in here. So for the UDP packet, the IP address will be changed from 10.1.0.3 to 10.1.4.3. So it's in here, 10.1.4.3. This is the packet. And for the port number, it will be changed from 2F99. So I think it's in here, like 2F99 here. And for the thread 2 and thread 3, it will change the payload from the last 7 here to 6 here. So it's shown here. And the 7 here to 6 is shown here. Yeah, so this is the simulation part.
Hello guys, welcome to the NetFPGA implementation of our design. So now I have successfully loaded the bit file for phase 1 of our project and started RKD. So next, we will look into how it works on the NetFPGA. My teammates have already explained how all the threads manipulate the network packet. So thread 0 changes the source IP address of node N0 into N1. It doesn't do that same to any other packets. Only in packets where the source IP address is N0, it will change the source IP address to N1. So now let us look how it works. So straight away, if you just try to ping N0, we will not see any response because due to the header checksums not matching and the reply being from a different source, the ping will not work. But on further inspection, we can look at those packets. But to make sure that the ping works on to other nodes, I will just ping N2. Yes, now we can see that the ping to N2 is working. So now I will demonstrate how we can we can show that the ping is of course working to N0, but is not we cannot able to see it. So basically, I will just run TCP dump for all the ICMP packets on N1, and next I will I will ping N0 one packet only. After pinging one packet only to N0, we do get a TCP dump, which is the reply from N0. But we can see that the packet has an error. What is the error? It has a bad checksum. Because we deliberately modify the source IP address in the header, we will have a bad checksum in the packet. So, and it says that the source IP address of of the packet which we captured using the TCP dump is 10.1.4.3, but it is not the case of node n0. The node n0, I will show the IF config for node n0. So the node n0 would be as an IP address of 10.1.0.3, but it says that we have got a reply packet for pinging n0 as 10.1.4.3. So that is what we have changed using our code. So this is the change for which is incorporated on the network packet by the thread 0. So next we'll look at the working of how thread 1 will modify the destination port by adding 1000x hexadecimal to the port to the destination port, and thread 2 and 3 will change the payload word 1 and thread 3 will change payload word 2. So first, let us look at the TCP working. All the TCP packets in our network processor will not be touched. So we'll not have any problems with the TCP packet. So now I will just shift to node N2. So I'll SSH into node N2. So after SSHing into node N2, we will try to have a server and a client communication between N1 and N2. So here I will start a server on port 8089, which is a TCP server. So after doing that, I will try to send a string to the same to N1 from N2. So we can see that the string 14 Ws is sent to node N1 from N2 and it is received by N1. So we can say that we are not modifying the source and destination IP addresses for TCP packets, and we are not modifying the source and destination port numbers for TCP packet. But in the case of UDP packet, I will demonstrate how it works in the case of UDP packets. So for that, we'll have to run two TCP dumps. One will be the real port where the packet is intended to go, and other will be the real and the another port where the packet where our thread will modify the network packet in such a way that the destination port is changed. So now I will just run the two TCP dumps. So first we will run the TCP dump on node N1. I will just SSH into N1. So I'm in node N1. I will just run the TCP dump on ports 8089. And here I will do the same, but on node N1 itself, I'll run another TCP dump, but this is on 12185. So you would be thinking, where are we getting this 12185 from? So once we convert the port number 8089 into hexadecimal and add 1000 hex to it, and we convert it back to decimal, we get this number. It is 12185. So it could be checked. So after running it, the two TCP dumps are already running. So what I would do, so here this experiment will demonstrate the working of three of our threads. That would be thread 1, thread 2, and thread 3. Thread 1, it will modify the destination port of the UDP packet. Thread 2 and 3 will modify the payload. So now after running the TCP dump, I will just try to send some data. This is through UDP, guys. So you can see it as dash U. So yes, oh, we got a UDP dump. But where? We tried to send it on 8089. Here we are running the TCP dump on 8089. Yeah, but we got it on 12185. This shows that our thread 2 is doing a very good job in modifying the destination port number of the network packet. So we can see that we have a bad UDP checksum. This is something we would like to improve in our further labs. I did try to disable the checksum checking in the system, but we unfortunately we did not have the right permissions to do so. So next, uh, we will look at the way our message is modified. So this is done by thread 2 and 3. So we sent the message with 14 Ws, but here we can see that the message is modified with WWFFFF. So W has an equivalent of hexadecimal of 77 in ASCII table. So that hexadecimal, we have converted it into 66. 66 being F is equal to F in hexadecimal. Sorry, from the ASCII table. So it is F, 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 F. This is the this work is done by thread number 2, and again this WWWW is again kept as the way it is, and next again it has been modified into F, 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 F. So we can check the total number of digits we have from the sender and the receiver. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14. We have 14 digits or alphabets here, and while sending we have 14 alphabets: W, 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 yeah, and so on. Yes. So we can see that the threads 2 and 3 have successfully ran its own process and modified the payload. But unfortunately, we cannot see the same thing on a server because the packet was dropped due to bad payload. And we would like to improve that on further labs where we can modify the network packet in such a way that we even add the right checksum to the packet. So that would be our further goals. But for now, we can see that the whole pipeline is working with our own custom processor, which will modify the network packet, which is a multi-core processor. And we have gained all the required and we have verified all our operations on the packet. Thank you so much, guys.